We're opening the files today on cosmic transformation.
Yeah.
Really focusing on how stars end their lives. When you look up, most stars seem pretty steady. They seem set for, a fairly gentle retirement.
That's right. Our sun, for instance, it'll eventually just sort of puff off its outer layers.
And then settle down as a white dwarf.
Right.
A long, cold fade out. It's the quiet path.
That is the quiet path, definitely. But that's really only for the average stars, the stellar middle class, you could say. When you get to the really massive stars, the heavyweights, well, their final act is something else entirely.
That's supernova.
The supernova. It's basically the most powerful and consequential event in the known universe. This kind of explosive death, it's responsible for creating the heavy elements, the building blocks for planets, and also the most extreme objects we know of.
So our mission for this deep dive is to really map out this catastrophic end stage. We're going to look at the amazing remnants they leave behind, explore the frankly bizarre physics of things like neutron stars, pulsars, black holes.
And then, maybe surprisingly, we'll connect these incredibly distant, violent explosions right back to the history of life here on Earth.
It's a huge scope. But let's start with just defining the scale. Because when people hear stellar explosion, they sometimes mix up novas and supernovas, don't they?
They do, and it's a crucial difference. A nova, which happens maybe 100 times a year in our galaxy, it's impressive, sure. But you're comparing, like, a firecracker to a thermonuclear bomb. It's just leagues apart.
That's a really good way to put it. So a nova is usually in a binary system,
Right.
like a white dwarf pulling material off a companion.
Exactly. It's a surface explosion, thousands of times weaker than a supernova, and critically, it can happen again.
Right. It's repeatable. The star itself isn't fundamentally changed.
Precisely. Novas are, surface events. They're contained. They don't drastically alter the star's core structure. They only blow off a tiny bit of mass, maybe like 10 to 3 to 10 to 5 of the sun's mass. The white dwarf is still there, ready to potentially go again later.
But a supernova, that's a one-shot deal, a unique catastrophe.
One and done. It's much rarer, maybe only once a century in a big galaxy like ours. And it means either a radical change to the star's structure or, well, it's total violent obliteration.
And the energy output difference.
It's just mind-boggling. A supernova can increase the star's brightness by hundreds of millions of times. For a little while, that single dying star can actually outshine all the billions of other stars in its entire galaxy combined.
Wow. That's hard to grasp. If you want a definition of cosmic power, that has to be it.
Absolutely. And because they're so rare statistically in our own galaxy, maybe once a century on average, astronomers can't just sit around waiting for one to pop off nearby.
Right, we'd be waiting a long time, so we look further afield.
We have to. We rely heavily on just systematically watching hundreds, thousands of other galaxies to catch these things in the act. Right now, we find maybe about 20 extragalactic ones each year.
And it's kind of ironic, isn't it? The last one we actually saw in our own Milky Way.
Kepler star, 1604.
Yeah, just before telescopes and spectroscopy really took off,
What?
we missed the chance to get a really good close-up look with modern tools.
Exactly. Bad timing, astronomically speaking.
But thankfully, people were looking up long before telescopes. Which brings us to one of the most, maybe the most important historical anchor point for all of this. We're talking about 1054 AD.
Ah, yes. The Chinese Chronicles, an absolutely priceless record. They meticulously documented the appearance of a guest star in July of 1054, and this wasn't just some faint new dot.
It was a spectacle, you said.
Oh, yeah. They recorded it as being brighter than Venus.
Brighter than Venus. That's the brightest thing in the sky apart from the sun and moon.
Correct. So this guest star was so bright it was visible during broad daylight.
During the day. For how long?
For several months, according to the records, before it gradually faded away. An incredible historical marker for a colossal cosmic event.
Okay, now fast forward. 7.5 centuries later, French astronomer Charles Messier is putting together his list.
His famous catalog of fuzzy things not to confuse with comets.
Right. And he catalogs this one particular object, kind of weirdly shaped nebula. He calls it Messier 1 or M1.
Which we now know, of course, as the Crab Nebula. The connection wasn't immediate, but as telescopes got better, astronomers studying M1 noticed something really vital.
He was expanding.
It was expanding. Slowly, yes, but systematically, you could measure it.
So then they did the math. They knew the distance, roughly.
About 2,000 parsecs, yeah. That's around 6,500 light years. Knowing the distance and measuring the angular expansion rate, lets you calculate the actual speed.
And the speed they found was
Astonishing. The gas in the Crab Nebula is flying outwards at 1,500 kilometers per second.
1,500 kilometers, just for context.
That's over 100 times faster than, say, our fastest satellites orbiting Earth, or Earth's speed around the sun. Normal gas clouds in the galaxy. They drift along at maybe 20, 30 kilometers per second. This was clearly from a massive explosion.
A giant explosion. And if you trace that expansion back in time,
Exactly. You run the clock backwards. 1,500 kilometers over roughly 900 years. It means all that gas must have started from a single point or a very tiny region.
right in the spot in the sky where the Chinese observers saw that bright guest star in 1054.
Precisely. The location matches, the timing matches based on the expansion rate. The case is absolutely solid. The Crab Nebula is the remnant of the 1054 AD supernova, history and physics coming together perfectly.
So the Crab Nebula is kind of our Rosetta Stone for this stuff. But it's not just its history that's special, is it? It's the way it shines. The light itself tells a story.
A very high energy story, yes. What really sets supernova remnants apart from just, regular old clouds of gas like the Orion Nebula is their powerful non-thermal emission, light that isn't just from heat.
And this was first picked up in radio waves.
Yeah, back in 1949, the Crab was found to be a really strong source of radio waves, and figuring out the mechanism behind that radio emission, well, it forced astrophysicists to realize something fundamentally new was happening in these remnants.
This is where synchrotron radiation comes in. Sounds complicated.
The name is technical, maybe, but the concept is actually tied to speed. It's the light you get when incredibly energetic electrons moving near the speed of light, so we call them relativistic, are forced to spiral around magnetic field lines.
So the magnetic fields in the nebula basically whip these electrons around.
Exactly. And every time they're forced to change direction, to spiral, they radiate away some energy as a photon. It's like a fingerprint saying extreme acceleration happened here.
Okay. And finding synchrotron radiation in the Crab Nebula meant
It meant that the supernova explosion itself must somehow create or accelerate a huge number of these super high energy electrons. These are essentially cosmic rays.
so this connects to the mystery of cosmic rays. Where do they all come from?
Precisely. This was a huge piece of the puzzle. People calculated, okay, how often do supernovas happen? Roughly once a century. How many cosmic rays does something like the Crab seem to contain or produce? You run the numbers, and it turns out supernovas are probably the main source, the primary engine, replenishing the galaxy's entire supply of these high-energy particles. They fill the whole Milky Way with them.
So they're cosmic ray factories. And they're also element factories, right? That's the other crucial role.
Absolutely vital. Supernovas are the cosmic forges. They create and blast out all the heavy elements, everything heavier than iron on the periodic table. Without them, the universe would be pretty boring, mostly just hydrogen and helium.
No carbon, no oxygen, no silicon, no iron.
No rocky planets, no us. This enrichment of the interstellar gas clouds is absolutely critical for forming later generations of stars, like our sun and the planets around them, and ultimately, for life.
Okay, back to the Crab's light. Because it wasn't just radio waves. There was a prediction in the 50s.
Yes, a bold prediction back in 1953, based on the synchrotron idea. The original source material we're looking at notes the author predicted that almost all, like 95% of the Crab Nebula's visible light, the light our eyes see, should also be synchrotron radiation.
So not just heat glow, but generated by even faster electrons.
Exactly. To get synchrotron emission up in the visible part of the spectrum, you need electrons with hundreds of times more energy than the ones making radio waves. We're talking energies up to 10, maybe even 10, 12 electron volts. That's enormous.
That sounds like a prediction you could actually test, though.
It was, and it's a beautiful example of theory leading observation. The theory said if this visible light is synchrotron, produced by electrons spiraling in magnetic fields, then that light must be polarized.
Meaning the light waves should vibrate more in one particular direction.
Correct. And lo and behold, subsequent observations by both Soviet and American astronomers shortly after the prediction confirmed it. The optical light from the Crab Nebula is strongly polarized. It was a huge confirmation of the whole synchrotron picture.
And then it went even higher energy, X-rays.
Yep. Starting around 1963, 1964, detectors sensitive to X-rays were pointed at the Crab, and bingo, powerful X-ray emission. And guess what?
Also synchrotron.
Also synchrotron radiation, which meant you needed even more energetic electrons, now pushing up to 1013 or 1014 eV. Just incredible particle acceleration going on.
So the Crab Nebula is this amazing energy powerhouse. But you mentioned its structure is a bit unusual.
It is, compared to many others. When we look at most older supernova remnants, like the one from Tycho Brahe's supernova in 1572, they tend to show a very distinct shell structure, especially in radio and X-ray light.
And that shell is basically the blast wave hitting the surrounding gas.
Exactly. It's the ejected outer layers of the star slamming into the interstellar medium, creating a shock wave that heats the gas to millions of degrees. It forms this expanding bubble or shell.
But the crab doesn't really look like that.
Not really. The crab and a few others like it are what we call filled center or plurionic remnants. The brightness is concentrated towards the inside, suggesting it's being continuously powered by something at its core. It doesn't have that clear outer shell.
So that difference in appearance, shell versus filled center, it must mean there are different ways for stars to blow up or different things left behind.
Precisely. It led astronomers to realize we needed to classify these explosions more carefully. Not all supernovas are created equal.
Okay, so the crab's unique look points towards different kinds of stellar deaths. And since we kind of missed the boat on studying recent galactic ones up close?
We had to rely on those hundreds of extragalactic ones we see each year to build up a picture. And from those observations, astronomers have basically settled on two main categories, two main types of supernova. They're distinguished by things like their light curves, their spectra, the chemical fingerprints, and where they tend to happen.
Let's start with type I.
Okay, type I supernovas. They seem to be linked to older stars, often stars that started out maybe only a bit more massive than our sun.
And you find them everywhere.
Pretty much. You see them in elliptical galaxies, which are full of old stars and haven't formed new ones in billions of years. You also see them in the central bulges and halos of spiral galaxies, again, older populations. They get incredibly bright, actually often brighter at their peak than type 2.
They don't throw off much stuff.
Paradoxically, no. They eject relatively little mass, maybe only a few tenths of a solar mass. The thinking now is that most type Is, specifically type Ia, are triggered by something happening to a white dwarf star, often in a binary system. Like maybe it pulls too much mass from its companion and tips over a critical limit.
Okay, so that's type Y. Then there's type 2, which sounds like the real behemoth killer.
Type 2 is the death of the true giants. These are the endpoints for the most massive, young, hot stars, the O and B class stars.
And you only find these where stars are actively being born.
Exclusively. You only see type 2 supernovas in the spiral arms of galaxies, where all the gas clouds and star formation are happening. It's thought that, yeah, a very large fraction of those really massive, hot blue stars end their lives as a type 2.
So this difference points to the core mechanism, right? What actually causes the explosion? Why does the star suddenly decide to detonate?
It's all about gravity winning its lifelong fight. You know, a star spends millions or billions of years in this delicate balance.
Gravity pulling in, pressure pushing out.
Exactly. Inward gravity wants to crush everything. Outward pressure from the heat and radiation generated by nuclear fusion in the core pushes back. As long as there's fuel to burn, that balance holds.
But eventually the fuel runs out.
It does. First hydrogen, then helium, then heavier elements in the core of a massive star. Once the fuel for the current fusion stage is exhausted, that outward pressure just drops almost instantly.
And gravity takes over.
Gravity wins. Catastrophically. The current understanding, especially for type 2 supernovas, is that the explosion is driven by the sudden, incredibly rapid release of gravitational potential energy. The star's inner core collapses inwards under its own weight.
A gravitational core collapse.
Right. This core collapse happens incredibly fast, forming something extremely dense at the center. Then, somehow the details are still debated, this collapse triggers a rebound or a massive shock wave that blasts outwards through the rest of the star. That's the explosion we see.
And what happens to that collapsed core? That comes down to mass again, doesn't it?
Mass is destiny, absolutely. It's the mass of the core after the star has blown off its outer layers that determines what's left behind.
So if the core is relatively small,
If the remaining core mass is below a certain limit, roughly 1.2 times the mass of our sun, the Chandrasekhar limit, then something called electron degeneracy pressure can actually halt the collapse.
degeneracy pressure, like the electrons just refuse to be squeezed any closer together.
Sort of, yeah. It's a quantum mechanical effect. If the mass is low enough, that pressure is strong enough to fight gravity to a standstill, and the star settles down into a stable, incredibly dense object. A white dwarf. That's the peaceful ending.
But if the core mass is above that 1.2 solar mass limit,
Then even electron degeneracy pressure isn't enough. Gravity keeps crushing. The pressure gets so immense that electrons are literally forced to combine with protons,
Making neutrons.
making neutrons. The star can't form a stable white dwarf. The collapse continues, catastrophically. And if the mass is in a specific range, let's say between roughly 1.2 and maybe 2.5 solar masses, that collapse halts again, but at a much, much higher density.
And that's when you get
A neutron star.
neutron star. The name itself sounds extreme. This is what happens when that core collapse goes further than a white dwarf.
Much further. You're talking about a core that might have started out bigger than the sun being crushed down into a sphere that's only about 10 kilometers across.
10 kilometers. That's like the size of a city. For something with more mass than the sun.
Exactly. Shrinking a star down to the size of Manhattan, basically. The resulting density is just, it's almost impossible to get your head around. 10-15 grams per cubic centimeter.
10 to the 15.
Yeah. A single teaspoonful, a sugar cube's worth of neutron star material would weigh about as much as Mount Everest. Or maybe all the mountains on Earth combined. It's denser than the nucleus of an atom.
Because it's basically made of neutrons packed together.
Pretty much. The gravity has become so strong, it's overcome the forces that keep atomic nuclei apart, and it's literally crushed electrons into protons to form neutrons. It's neutronium, essentially.
Okay, so theorists figured this out,
Yeah.
that these things should exist. But finding one, that seemed like a huge challenge,
And
especially in visible light.
an absolute nightmare, observationally. I mean, think about it. Even if a neutron star was pretty hot, say 6,000 Kelvin surface temperature like our sun, its radius is tiny, maybe 100,000 times smaller than the sun.
So the total light output would be minuscule.
10 billion times fainter than the sun. You'd never see it in visible light, even if it were right next door.
So the hope shifted to X-rays, right? Because they should be incredibly hot right after they form.
That was the thinking, yeah. The collapse generates unbelievable heat. The initial surface temperature could be up to 1 billion Kelvin. That should produce a phenomenal blast of X-rays, maybe 1045s per second, just enormous power.
Yeah.
But they cool down incredibly fast, mostly by spewing out neutrinos, which just zip straight out of the star, carrying energy away. Within months, the surface temperature likely drops below 10 million Kelvin. The window for detecting that initial thermal X-ray glow turned out to be really, really short.
So by the mid-1960s, people were getting a bit pessimistic about actually finding one?
There was definitely some disappointment, yeah. The X-ray searches hadn't panned out as hoped. And then, as seems to happen so often in science,
The discovery came totally by accident.
completely by accident and from a totally different direction, radio astronomy. This is the famous lightning bolt discovery of 1967.
Jocelyn Bell Burnell.
Jocelyn Bell, yes, who was then a graduate student working with Anthony Hewish at Cambridge. She was analyzing data from a new radio telescope designed to study quasars, and she noticed this weird signal. Scruff, she called it.
Not noise, not interference. Something else.
Something else entirely. It wasn't steady, it wasn't random noise, it was these incredibly brief, sharp pulses of radio waves.
And the key thing was the timing.
The timing was astonishing, strictly, rigorously periodic. One source was pulsing exactly every 1.337 seconds. Tick, 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 like clockwork.
That must have been baffling.
It was so unnatural, so regular, that they genuinely, for a short time, couldn't rule out, well, artificial signal.
The LGM hypothesis. Little green men.
That's right. They kept it quiet initially, partly because the idea seemed so outlandish, until they found a second pulsing source, then a third, then a fourth, all with different but incredibly stable periods.
But multiple LGMs seemed unlikely. What could naturally produce such a precise clock?
That extreme regularity, accurate to maybe 1 part in 100 million, ruled out almost everything. Planets orbiting, stars pulsating normally, nothing fit. The only thing that could spin that fast and that steadily had to be a super dense, compact, massive object rotating incredibly rapidly.
A rotating neutron star.
A rotating neutron star. The objects were dubbed pulsars. And the final confirmation came when they found the real speed demons.
The really fast ones.
Exactly. When a pulsar was discovered with a period of just 0.033 seconds that's spinning 30 times a second, the physics became undeniable.
Because things can't spin faster than light.
Right. Basic physics says the equator of a spinning object can't exceed the speed of light. For something spinning 30 times a second, you can calculate the maximum possible radius it could have without flying apart or violating relativity. And that maximum radius
Only a few tens of kilometers.
had to be a neutron star. There was nothing else it could be.
And the absolute clincher, the smoking gun, was finding that fastest one, NP MP0532,
Located smack dab in the center of the Crab Nebula.
the remnant of the 1054 supernova.
Exactly. The pulsar was right where the original star exploded. That locked it in. Pulsars are the rapidly spinning neutron stars created in supernova explosions.
Okay, let's talk about that spin. How does a star that might rotate once a month suddenly end up spinning dozens or hundreds of times a second?
It's a classic physics principle. Conservation of angular momentum. Think of an ice skater pulling their arms in to spin faster.
Right, same amount of spin energy, but concentrated in a smaller radius so the speed goes up.
Precisely. Now scale that up astronomically. Take a normal star, maybe like our sun, rotating slowly. Now imagine its core collapses catastrophically. Its radius shrinks by a factor of, say, 100,000 times from hundreds of thousands of kilometers down to just 10 kilometers.
Okay.
Conservation of angular momentum dictates that its rotational speed must increase by that same factor 100,000 times.
Wow. So its equator would be moving incredibly fast.
Close to the speed of light, potentially. And the rotation period, how long it takes to spin, once decreases by the square of that factor. So roughly 100,000 squared, which is 10 billion times shorter.
10 billion times. So a month-long period becomes
Less than 1,000th of a second. The neutron star is born spinning unbelievably fast.
And it's not just the spin that gets amplified, is it? The magnetic field, too.
Even more dramatically, actually. The magnetic field lines get compressed along with the collapsing matter. The physics says the field strength, H, goes up as the inverse square of the radius, propto R2.
So if a radius shrinks 100,000 times,
The field strength increases by 100,000 squared. That's 10 billion times stronger. So even if the original star had a pretty weak magnetic field, say 100 Gauss,
neutron star gets a field of
1012 Gauss, a trillion Gauss. These are the strongest magnetic fields known in the universe.
I can't even begin to imagine what a field that strong is like.
It's hard to picture. The energy stored in that magnetic field is so immense. The energy density itself is equivalent to a mass density of maybe 50 grams per cubic centimeter.
Denser than lead, just from the magnetic field energy.
Denser than any substance on Earth, yeah. That field completely dominates the environment around the neutron star.
And this spinning, supermagnetized object is what powers the pulsar emission, the lighthouse model.
That's the leading theory, yes. The magnetic poles are offset from the rotation axis. The intense magnetic field and rapid rotation somehow generate beams of radiation radio waves, mostly that shoot out from the magnetic poles.
Like a lighthouse beam.
Exactly. As the star spins, these beams sweep across space. If one of those beams happens to sweep across Earth, we see a pulse of radio waves every time the beam points our way.
Makes sense. And the Crab pulsar, MP0532, it's special even among pulsars, isn't it?
It really is. To this day, it's the only pulsar we know for sure emits pulses, not just in radio waves, but also in visible light and X-rays.
Seeing optical pulses from it must have been tough. It's faint, right?
Very faint, about 16th magnitude.
Yeah.
Detecting its optical pulses back in 1969 was an amazing feat of observational ingenuity. They actually used a stroboscope, basically a spinning disk with slits timed perfectly to the pulsar's period.
To kind of freeze the light.
Yeah, to block the light when the pulsar should be off in its cycle and let it through when it should be on. And it worked. They proved that faint little star at the heart of the nebula was indeed blinking on and off 30 times every second.
Wow. And just like the nebula's light, the pulsar's optical light isn't just heat, is it?
Nope. It's also synchrotron radiation. But here's a fascinating detail. That optical and X-ray light doesn't seem to come directly from the tiny neutron star surface itself.
Where does it come from, then?
It seems to originate from its extended magnetosphere, the region around the star dominated by that enormous magnetic field, which is probably hundreds of times bigger than the neutron star itself.
So the pulsar isn't just a dead cinder. It's actively accelerating particles out in its magnetic environment.
Exactly. It tells us the pulsar is the engine. It's continuously accelerating particles up to those incredible 1013 eV energies. And it's those particles interacting with the magnetic fields that light up not just the pulsar's immediate vicinity, but the entire surrounding Crab Nebula. It powers the whole thing.
Okay, so we have two possible endpoints for massive stars after they explode. If the leftover core is below about 1.2 solar masses, it becomes a white dwarf. If it's between maybe 1.2 and 2.5 solar masses, it stabilizes as a neutron star.
Right. Supported by electron degeneracy pressure in the first case and neutron degeneracy pressure in the second.
But what if the core is even more massive than that? What if it's above roughly 2.5 solar masses? Can neutron pressure hold it up then?
No. That seems to be the upper limit. Current physics suggests there is no known force, no form of pressure, that can withstand the relentless crush of gravity if the remaining mass is greater than about 2.5 times the mass of the sun.
So there's nothing left to stop the collapse.
Nothing. The star must undergo complete runaway gravitational collapse.
And this isn't a slow process.
Not at all. Gravity just takes over entirely. The star gets crushed inwards at incredible speed, potentially squeezing all that mass down towards a single point, a singularity, in potentially just fractions of a second.
As it collapses, its gravity gets stronger and stronger. And the escape velocity.
The escape velocity, the speed you'd need to escape its gravitational pull, climbs rapidly. And this is where general relativity really becomes crucial. There's a critical point.
The point where the escape velocity reaches the speed of light.
Exactly. $6. Light itself can no longer escape. That critical radius is called the Schwarzschild radius.
Named after Carl Schwarzschild, who calculated it from Einstein's equations.
Right. Just for scale, if you could somehow crush our sun down to its Schwarzschild radius, it would only be about 3 kilometers across. The density at that point would be immense, like 1016 grams per cubic centimeter.
So anything that collapses inside its own Schwarzschild radius is trapped forever.
Trapped forever. This radius defines the boundary, the event horizon of what we call a black hole.
And this is where time itself starts doing very strange things, isn't it? Especially for someone watching from the outside.
Yes, time dilation becomes extreme near the event horizon. Imagine the classic thought experiment. An astronaut is falling into the black hole. Let's say they send out a pulse of light, a radio signal, once every second according to their own watch.
Okay.
As they get closer and closer to that Schwarzschild radius, the signals we receive back here on Earth would arrive further and further apart in time.
Because the gravity is stretching space-time, slowing down time relative to us.
Exactly. The 1-second interval on the astronaut's watch might become minutes between signals for us, then hours, then years, then centuries.
So, do we ever actually see them cross the event horizon?
According to general relativity, from our external perspective, no. The signals would get infinitely stretched out in time, infinitely redshifted. The astronaut would appear to slow down, freeze, and fade away just as they reach the horizon, but never quite cross it. The light from that final moment takes an infinite amount of time to reach us.
Wow, so the object just seems to hover there, becoming infinitely dim. That's the black hole.
That's the black hole. Or as the physicist Yakov Zeldovich apparently called it, a gravitational tomb. Nothing, no light, no particles, no information can get out from inside the event horizon. The only way it interacts with the rest of the universe is through its gravity.
It's such a bizarre concept. A region of space-time where gravity is so strong, it seals itself off. And that idea that we never see the final collapse happen, it does make you wonder, doesn't it? From our universe's perspective, does it ever truly finish?
It definitely pushes the boundaries between physics and philosophy, but it's important to add a caveat. This picture of collapse to a perfect point, a singularity, assumes the star isn't rotating.
Rotation complicates things again.
As it often does. If the original star is spinning rapidly as it collapses, that spin gets amplified enormously, just like with neutron stars. The centrifugal force at the equator could become so strong.
It could resist the collapse.
It might. It could potentially prevent the star from collapsing all the way to a point singularity. Maybe it flattens into a rapidly spinning disk, or maybe it even fragments and breaks apart before reaching the Schwarzschild radius for its total mass. So perhaps only stars that start out rotating very slowly are truly destined for that singularity fate. The role of rotation in the final stages of collapse is still a really active area of research.
Okay, we've mapped out the dramatic fates of massive stars. Now let's bring this back home before anyone gets too worried. Let's just state it clearly again. Our sun is not going to do this right.
Absolutely not. Our sun is far too small, way too low in mass, to ever explode as either a Type I or a Type II supernova. We are perfectly safe from our own star in that regard. Its end will be much quieter.
Phew. Okay. But the galaxy isn't necessarily safe, is it? We know these explosions happen. So the big question is, what's the chance that one has exploded close enough to Earth sometime in our planet's long history to actually affect life here?
That's a critical question, and astrophysicists have tried to estimate it. It involves a bit of probability calculation, basically.
You need to know how often they happen and how big the galaxy is.
Pretty much. We take the rate of Type II supernovas, remember, those are the massive star deaths, which we estimate is roughly 1 every 100 years in a galaxy like the Milky Way.
Okay, once a century.
Then you estimate the volume of the galactic disk where these massive stars live. Let's say a disk with a radius of 10,000 parsecs and maybe 100 parsecs thick. Then you define a danger zone. How close does a supernova need to be to potentially cause problems? Let's pick a distance, say 10 parsecs.
10 parsecs, that's about 33 light years. Seems reasonably close, astronomically speaking.
Right. So you calculate the volume of that danger sphere around the sun, and you figure out the probability of a supernova occurring within that volume given the overall rate in the galactic disk.
And the number that comes out is?
The calculation suggests that a supernova within that 10 parsec range should occur, on average, about once every 750 million years.
Once every 750 million years.
Okay.
And Earth is about 4.55 billion years old.
Exactly. So just based on statistics, it's not just possible, it's actually quite likely, maybe even statistically certain, that the solar system has experienced such a nearby supernova event, probably several times over Earth's geological history.
Wow. Okay, so it's happened. What are the consequences when it does? Let's imagine a star 10 parsecs away goes supernova. What happens here?
We can break it down into maybe two phases. First, there's the initial flash of light and radiation.
How bright would it be?
It would be incredibly bright, millions of times brighter than Sirius, which is the brightest star we normally see.
But still much fainter than the sun.
Oh yes, still about 10,000 times less bright than the sun. So it wouldn't instantly fry the Earth's surface, but night would become incredibly bright. It would light up the landscape, maybe 100 times brighter than a full moon, possibly for weeks or months.
Okay, bright nights. What about the dangerous radiation? UV, X-rays?
That's the more immediate concern from the flash. There would be a huge burst of high-energy ultraviolet radiation, probably tens of times more intense than what we normally get from the sun.
That sounds bad.
It would definitely cause significant ionization high up in the Earth's atmosphere. But, crucially, our atmosphere, especially the ozone layer and the upper layers, is actually very effective at absorbing this kind of radiation. It would likely absorb almost all of it, preventing an immediate biological catastrophe down on the surface. So we'd probably survive the initial flash, albeit with some potentially dramatic atmospheric effects.
Okay, so the flash isn't the killer. What's the second phase? The long-term effect.
The long-term effect comes from the actual stuff blown off by the star, the expanding supernova remnant, that shell of gas and magnetic fields and high-energy particles we talked about.
That doesn't arrive instantly, does it?
No, it takes time to travel those 10 parsecs. Even moving at thousands of kilometers per second, the expanding shell, the radio nebula, would probably reach the solar system maybe 10,000 years after the initial explosion.
And then we fly through it.
Yes. The Earth and the entire solar system would then be immersed inside this remnant, this cloud of energetic particles and magnetic fields, for a very long time, potentially for tens of thousands of years as we pass through it.
And because these remnants are full of cosmic rays.
Exactly. While we're inside that remnant, the density of primary cosmic rays hitting the top of our atmosphere would increase dramatically.
How much?
Estimates suggest maybe many dozens of times the normal background level we experience today. And there could be periods lasting maybe centuries where it could be even higher, perhaps hundreds of times the normal level as we pass through denser clumps within the remnant.
Okay, a sustained massive increase in cosmic radiation for potentially tens of thousands of years. That sounds like it could have biological consequences.
It absolutely could. This increased flux of hard radiation reaching the surface, or at least penetrating deeper into the atmosphere, acts as a powerful mutagen. It increases the rate of genetic mutations.
For organisms with fast life cycles, maybe it doesn't matter so much.
Probably less so, yeah. But for long-lived species, especially complex animals with slow reproduction rates and maybe specialized adaptations, they could be much more vulnerable.
Like dinosaurs.
Like dinosaurs, or large mammals. For some of these species, studies suggest that even a sustained increase in the background radiation dose by a factor of just 3 to 10 might be enough to double their natural mutation rate.
So if the cosmic ray level goes up by, say, a factor of 10 or more and stays that way for decades or centuries.
The biological consequences could be severe. Increased rates of cancer, genetic defects, reduced fertility. For highly specialized species already may be under pressure, it could potentially be catastrophic. It could lead to population decline or even extinction.
And this isn't just theoretical, is it? There was a specific hypothesis linking this to a major extinction event.
Yes. Back in 1957, the hypothesis was proposed that the mass extinction event at the end of the Cretaceous period, the one that famously wiped out the dinosaurs about 66 million years ago, might have been caused, or at least significantly contributed to, by exactly this mechanism.
A nearby supernova.
A nearby supernova, perhaps exploding only 5 to 10 parsecs away, bathing the Earth in intense cosmic radiation for thousands of years, leading to the collapse of delicate ecosystems and the extinction of many species, including the large reptiles.
So stellar death in deep space could directly drive mass extinctions on Earth. It's an incredible connection.
It is, but it might be a double-edged sword, too.
How so?
Well, while high radiation can be destructive, some have also speculated that maybe much earlier in Earth's history, billions of years ago, a period of enhanced radiation from a nearby supernova could have actually helped kickstart life.
By providing energy.
By providing energy to drive the chemical reactions needed to form complex organic molecules from simpler inorganic ones. So maybe these stellar catastrophes are not just agents of destruction, but also potential catalysts for creation, at least in the very early stages of life's emergence.
So we've journeyed from the explosive death throes of massive stars, through the bizarre physics of neutron stars and pulsars, to the very edge of gravity with black holes, and we've seen how these incredibly distant events can leave remnants like the Crab Nebula and potentially even influence the course of life here on Earth through cosmic rays and maybe even extinction events. It really ties the universe together.
It absolutely does. The life cycle of stars is intimately connected to our own existence and history. But we want to leave you with one final, kind of intriguing, maybe a slightly unsettling thought. An
That's
anomaly.
an anomaly related to these nearby supernovas.
Related to cosmic rays, yes. For decades, radio astronomers have known about something called the radio tongue, or sometimes the North Polar Spur.
The radio tongue, what is that?
It's this huge, unexplained arc or streak of faint radio emission that stretches across a large part of the northern sky, almost perpendicular to the plane of the Milky Way. It's enormous on the sky.
We don't know what it is.
Well, back in the 1960s, an English radio astronomer named Brown put forward a hypothesis. He suggested that this giant radio structure might actually be the faint, glowing shell of a very old, but also very close, supernova remnant.
How close are we talking?
He proposed it might have exploded only maybe tens of thousands of years ago and perhaps only 30 or 40 parsecs away, much closer than the 750 million year average event we calculated earlier. Because it's so close, it would appear huge on the sky like this tongue.
Okay, if that's true.
And there is some supporting evidence. More recent observations have found enhanced soft X-ray emission coming from that same general area of the sky, which could fit with a hot nearby remnant bubble. If this hypothesis is correct, it means the solar system might have passed through this ancient remnant relatively recently, or we might even still be sort of inside its tenuous outer edges right now.
Wait, if we're inside an old supernova remnant,
It would imply something profound. It would mean that the normal background level of cosmic rays that we measure today, the baseline we used for all those calculations about mutation rates and extinction risks, might not actually be the true galactic average at all.
it might be anomalously high because we're still feeling the effects of this nearby recent explosion.
Exactly. Our local environment could currently be permeated by lingering high-energy particles from this ancient stellar death.
So here's the final thought we want to leave you mulling over. What does it mean for our understanding of evolution, for genetic stability, even for the origin of life, if the cosmic radiation level we consider normal today is actually the lingering echo of a stellar catastrophe that happened practically in our backyard, cosmically speaking? What if we are right now living within the faint but tangible shadow of a cosmic tomb?